The central limit theorem says that the mean is approximately normally distributed under certain conditions. Okay, and so practically what that means is that if you got a data set like this, like maybe this is precipitation, you got a lot of days with no rain, some days with heavy rain, a lot of zeros. You made a histogram, if you keep going, it'd certainly not be bell-shaped, right? It wouldn't be approximately normally distributed. But if you were to take a mean of that data set, so let's say we gathered, like that data set kept going, we gathered 30 random data points, and we found the mean precipitation was 0.9. And then we did that again, we gathered 30 more random data points, we got 0.8. Mean 3 maybe is a little bit higher. Mean 4 is 1.1. If you kept going, the means would be approximately normally distributed. If you were to put if you kept going and you made like 40 or 50 means and you put those in a histogram, it would be approximately bell-shaped. So the data itself is not bell-shaped, but the means can still be, the means of the data set will be bell-shaped. That's what the central limit theorem guarantees us, as long as you take enough data points. Okay, so there's that condition. You got to have enough data points, because if you find a mean of just two numbers and you keep doing that, then you're going to get some outliers some of the time. It's not going to be bell-shaped. It's still going to roughly look like this distribution. Okay, so that's the idea, is that if you were to take a whole bunch of means, they would make a bell-shaped curve, even if the original data set doesn't make that bell-shaped curve. That's the central limit theorem. This question is talking about home prices. So before you try to decide whether the central limit theorem kicks in, the central limit theorem needs a large enough sample size. So this real estate agent is assigned 10 houses. That's not a big sample size. Okay, so the mean price of the homes we can't assume is normally distributed with the central limit theorem, because the textbooks that we use tend to just say 30 is the magic number. At least 30 data points. You could maybe have 35, or you could have 25, and then the means would be approximately normal. But you need approximately 30 to assume that the mean is going to be normally distributed. You need about 30 data points to assume that your mean is normally distributed. Okay, so that's why we're digging into this data more. We have only 10 houses, so we can't assume that the mean price is going to be approximately normally distributed. I'm trying to think of why they want to know whether it's bell-shaped or not. But would you expect the distribution of sales prices to be A, is prices tend to be about the same in any given area? That's not true, because you have different size houses, unless you live in a community where every house is the same. Okay, so I guess some people do live in those communities, so A is kind of a confusing option for those people. But the community I live in, the house next to me is almost abandoned. There's a house that's 2 houses up that's really nice, way more expensive than my home. So not uniform in most communities. B, prices tend to increase over time, so the distribution will be skewed to the right. Now that's true, except there's sometimes market downturns, right? So the options that are assuming knowledge about the housing market make me suspicious, okay? For my stat lab, this is the only one that doesn't assume any prior knowledge about housing, okay? This one is something that we can safely assume, more safely than all the other ones. You can't sell a house less than $0, but there's no cap on home prices, right? So when that happens in statistics, when there's a lower bound, but there's no upper bound on the prices, then we have to be looking for a right skew. So D is the correct option here. C would be correct if price was discrete, but it's really not. It should be a continuous variable. Discrete means countable, like you have 5 deer accidents, 10 deer accidents on a day, 3 deer accidents on a day. That's a discrete variable. Price is continuous because there's a lot of, there's almost an infinite amount of different prices you could have. Okay, so A is not always true. That's why I ruled that out. B, prices tend to increase over time, so the distribution will be skewed to the right. That's usually true, but it depends on knowing the housing market, and it depends on, sometimes it's not true, even if you do know the housing market. But since this one relies on specific knowledge about the housing market, that's not the correct answer we're looking for here either. This is telling us that our distribution will be skewed right, because there's a natural limit to how low they can go, but no limit to how high a home price can go. Okay, so it's skewed. It's skewed to the right, just like my precipitation data set down here. That means, if we need to be assured that the mean is normally distributed to do some statistics with it, some conditions have to hold. Okay, this next part's a bit frustrating as a statistics teacher about these assumptions. Usually, we want to randomly select things in statistics, because randomly selecting things helps us to assume that the data points are independent. Okay, but for this particular question, they want you to say that they are independent, assume that they're independent, but they're being picky, because it doesn't necessarily have to be random selection. If you have a data set, it's still kind of random though, I guess, whichever way you do it. Because I was thinking, if you do some sort of systematic sampling, you'd still have to assume that the data is shuffled. But the whole reason we do random selection is to make sure that prices or numbers are independent of one another. Picking one home doesn't impact our chances of picking a price for another home. Okay, so they don't want you to select randomly selected, but if you Google conditions of the central limit theorem, you're going to see that randomly selected is a condition. So I'm not super excited about them not checking off A, and I don't understand fully why they put that in there if it's so confusing. So yeah, usually you want random selection, and that's to help you assume that they're independent. Let's see, the distribution of prices must be assumed to be not too skewed and without outliers. So this isn't always the case. You don't necessarily need this for the central limit theorem. Okay, but this particular example, we need this condition to be true because we have a small sample size. We only have 10. If we had a sample of 100, then we don't really care what the underlying distribution is, because the central limit theorem says that the means will be approximately normally distributed. So if you have a sample size of 1 billion, and if you take many sample means like that, you're going to see almost a perfect bell-shaped curve. As sample size gets larger, the mean gets more and more normally distributed. So since our sample size is small, then we have to assume that the underlying distribution is approximately normal. Option 1 is, it is not reasonable to assume that prices are independent. I kind of think that's true, because when I moved from one house to another, I looked at the home prices around me, and I used those home prices to make a decision on my price. It wasn't independent. I wasn't using independent thought. I was depending on what other people are selling their home for. But they don't select this. They don't say that this is valid. That's pretty crazy. That assumes. Is not reasonable to assume the prices are independent. I think that's true. I think it's not reasonable to assume that the prices are independent. I think it's reasonable to assume they're dependent. But whatever. I guess we have to do what my stat lab says. It is not reasonable to assume the houses are randomly selected. I think it's reasonable to assume the houses are randomly selected, but I'm thinking about it being a realtor. Maybe only certain types of people go with one realtor and one go with the other, and therefore they're not randomly selected. But the realtor's getting these randomly assigned to them, I think they said at the beginning, right? Yeah, 10 houses at random. So they told us that. They told us the houses are randomly selected for them. So that's not true. So that one's okay. It's just this top one I'm not thrilled about. It is not reasonable to assume that there are no outliers. Can we assume that there are no outliers? No, we cannot. So this is a true statement. Right? And that's because of what we answered at the beginning. there's a natural floor to the prices. There's no natural ceiling. So that means there's likely to be one outlier. Okay. I remember when we were looking at houses, we watched the market. We had a good idea for price, and somebody put a home. There's two people that put homes in the same neighborhood. One was $100,000 more than the other, and it had about, I don't know, 200 more square feet. Right? They were an outlier. They were hoping for something more than what they were never going to get because they ended up dropping the price. But there's outliers because there is no natural ceiling to these numbers. There's bound to be an outlier. It's reasonable to assume that there are outliers. I hate the double negative. I mean, who screens these questions? Isn't that an English thing? Don't say double negatives because, like I just did. No, maybe I didn't. But this is confusing because there's an easier way of saying the sentence. It is reasonable to assume that there are outliers. It's not reasonable to say that there's not any outliers. I think I'm going to hit that button that says Ask the Publisher.